We need to use BFS in this case, because what we want to do is finding the shortest path. And in this case, we're just increasing our coverage step by step. And as we increase our coverage, and once we reach the end, that means we don't have to increase our coverage any longer. And we find the minimum or the shortest path using BFS. However, in the DFS, it goes to the end, and we need to check all the endpoints and compare them. It's going to be less efficient than BFS when it comes to finding the shortest path. So we're going to use BFS for this problem. And to solve this problem, we're going to make a visited node like this. However, because this one is 2D grid, we need to make 2D visited array like this. So we need to make 2D visited grid that has the same shape as the input grid. And we are going to make a queue using deck. And to this queue, we are going to append the starting point like this. So this starting point signifies the x coordinate and y coordinate. And here, the last element represents the number of edges at the number of nodes we have visited. And because we are starting from the top left position, we have visited only one vertex or node. And another thing we're going to define is a dx and dy array. I'll explain this one after I show you how we define this dx and dy. So we are going to get some position x and y and add dx and dy to our current position. And this is going to be new x and new y. And here, the first one is 1 and 0. This means, let's say the current position is this position, and 1 and 0 means dx1 and dy0 means we are going downward. And in the y direction, we are not moving. So in this way, we can check all the neighbors. And in the case of less one, -1 and 1, this means, let's say this one is the current position, then we are moving in the minus direction like this. And then in the y direction, we're moving upward, downward like this. So we're decreasing x1, increasing y1. So this one, the last element, means left bottom diagonal neighbor. All right. Once I implement this one, the meaning of dx and dy will be more clear. And while our queue is not empty, what we are going to do is retrieve these three numbers from our queue. And if the current grid is x and y equals 1, then we cannot move to this position because we can only step on zeros. So we're just as this case. And if x is the length of grid -1, and if y equals the length of grid 0 -1, then this means we have reached the bottom right. So we're going to return B. this distance. Okay, we're keeping track of the distance. Otherwise, we're going to mark this X and Y position as visited. And for current X and current Y, what we are going to do is make new X and new Y like this. Okay, so by making this for loop simple, we can inspect all the neighbors. Otherwise, we need to make like nx1 equals x plus 1 and y1 equals y plus 0. And we need to make this kind of expression over and over to investigate all the neighbors. So by defining this dx and dy, we can make the process of inspecting all the neighbors very simple. And if this new nx is in the correct boundary, and y, ny is in the correct boundary, and if this grid nx and ny has the value of 0, and this one is not visited, then what we're going to do is append this position to our queue. However, we need to increase the distance by 1 because we are visiting one more node. And after inspecting all the possible cases, if we cannot reach the destination, then we're going to return -1. Okay, so this is very common problems if you are going to prepare for coding interviews or coding tests. Okay, up to this point, any questions? Cool, let's move on. From now on, we're going to talk about minimum spanning trees. First of all, what are minimum spanning trees? And we abbreviate minimum spanning trees as MST here. First, spanning trees is a connected subgraph in an undirected graph where all vertices are connected with the minimum number of edges. In this example, we want to connect all nodes and if we connect A and B, so A and B are connected. If we connect A and C, A and D, and A and E, then all the nodes are connected, and we are using the minimum number of edges to connect all the components. However, you can also use these connections, A and E, A and B, B and C, C and D. This one also uses the same minimum number of edges and can successfully connect all the edges, all the vertices. So as you can see here, spanning trees are not unique. There can be multiple spanning trees. Okay, so undirected graph can have multiple spanning trees. Now let's talk about minimum spanning trees. Minimum spanning trees is a spanning tree with the minimum possible total edge weight in a weighted undirected graph. So what does it mean? In the previous case, the edges does not have any values. However, in the case of weighted undirected graph, edges have some values like this. And we want to find the minimum spanning tree that has the minimum possible total weight, edge weight. And we have many applications for MST. Let's say we want to visit some cities like A city, B city, C city, D city, E city. And we need to visit all these positions. Or you can think about 택배. You need to deliver some items. Then you want to move, saving all the possible resources. In those cases, you need to come up with the minimum possible total weight. And there are two algorithms to find minimal spanning trees. The first one is Cross-Gall's algorithm, and the second one is Prim's algorithm. And in this class, let's talk about Cross-Gall's algorithm first. The overall procedure is like this. We are going to sort all edges in the ascending order, and then add edges in that order into the MST. And we are going to skip some edges that will produce cycles. And repeat these two processes until we make n minus n edges are connected. So in this example, we have multiple edges. And this one signifies connecting 3 and 5, and the weight is 18. So we are sorting the edges before we perform Cross-Gall's algorithm. And what we do is choose the minimum edge one by one. We are going to choose 3, 5, 18, this edge first. And then the next step is 1, 2, because this one has the next minimum weight, 21. And we're going to choose 2, 6, this one. And 0, 2, this one. So we have chose this one, this one, this one, this one. And the next item we need to think about is 0, 1, which has 32, the weight of 32. However, if you choose this one, then this will create a cycle here. So we are just skipping this part and move on to the next one. Okay, so we are connecting these two nodes. And we're also skipping this one because it's going to create a cycle like this, 4 and 5. So we're skipping this one. And we choose the next one like this. So in this way, we can connect all the vertices using the minimum weight. So a pretty simple algorithm when you just look at this one using this figure. So let's implement this algorithm together. Cross-Gall's algorithm. Okay, we're going to implement Cross-Gall's algorithm. Okay. So as in the previous case, DFS and BFS, I'm going to just show you a pseudocode, and you're going to implement the actual Cross-Gall algorithm in the PPP exercises. Let's say we're given a graph, and this graph has the form of vertex A and vertex B and weight, a set of these nodes, edges. And we're going to create a minimal spanning tree. And here we're going to use disjoint sets. And we're going to make n disjoint sets because we have n nodes. And we're going to sort the edges according to the weight. Let me move that. And the criteria is going to be this one, the weight. So we pass the criteria in this way. And MST cost is going to be 0 at the beginning. And while the length of MST is smaller than n-1, we retrieve 2 nodes and the weight. And we pop the first element from our nodes. And if these 2 nodes are not connected, we're going to union U and V. And then we are going to append U and V to our MST. And MST cost increases by val. So this is pretty simple, okay? And I'm going to give you the last PPP exercise of today. Okay, so this is our last exercise. We are going to implement minimum cost connections. So I'll just give you the description of this function. The input is some points, so 0, 0 to 0.2, 2, 3, 10. And what we want to find is the minimum distance to connect all these points. So here, this is the configuration of minimum weight. However, we're going to use not Euclidean distance. However, we are going to use Manhattan distance. So what is Manhattan distance? Let's think about these 2 points. The distance between these 2 points is, in the case of Manhattan distance, we go to the x direction 2 and then y direction. So the distance between these 2 points is 4. However, in the Euclidean distance, it's going to be √8. However, we are not using this Euclidean distance. And the distance between this point and this point is 5 plus 2. So we are using x direction and y direction to calculate the distance. All right. So we want to find the minimum weight to connect all these nodes, all these points. And solving this problem can be quite tricky. So I'll give you some hints here. And you can use this edge class to solve this problem. And it will ease the implementation. So have a look at these hints and try to use this edge class to solve this problem. In fact, we are running out of time, so this is going to be our final homework. And I will start from this point in the next class.